short review about logarithms and some of their properties. When you see something like this question, what is this word log, a little 2 as a subscript, and then the number 8. We say, what is log base 2 of 8? And what that means is, or that's the same question as asking, 2 to the what power is equal to 8. Those are same question, written in a different way, and they have the same answer, which of course is 3. 2 to the third equals 8. So when you see something like log base b of a equals, something, I'll call it x, that's equivalent to saying b to the x equals a. Those are two ways of saying the same thing. So log base 2 of 16 would be 4, because 2 to the 4th equals 16. If I change the base, log base 4 of 16, that's a different answer, because this is asking 4 to what power equals 16. That one's just 2. The most popular base is log base 10. Log base 10 of 100 is 2, because 10 to the second power is 100. Log base 10 of 1,000 would be 3, because 10 to the third equals 1,000. But if I do log base 10 of something like 500, we can't say without a calculator what that is. It's something between 2 and 3, we know that. Seems like it's probably closer to 3, because 500 seems to be closer to 1,000, but we don't really know. Well, on our calculator, there is a log base 10 button. It's just, and very often, if you see no number, if you see no number there, it is implied to be log base 10. So on your calculator, if you type in log 500 and hit enter, it's going to say about 2.7, and that's because 10 to the 2.7 equals 500. For other bases, some calculators have a function for other bases. Like here, I say log base 3 of 81. That equals 4, because 3 to the 4th equals 81. On the TI calculator, if you push math and then you push the A key, it will make a little thing that says log, a little box here and a little box there, and you could actually type in any two numbers you want and hit enter, and it will calculate it for you. Log base 2 of 2 is 1. That's 2 to the 1 equals 1. And log base 2 of 1 is actually 0, because 2 to the 0 equals 1. And that's actually true for anything, like log base 5 of 1 is also 0, and log base 10 of 1 is also 0. But if you try to, you could even do log, like here's something like log base 4 of something less than 1, like 1 over 64. That equals negative 2, because 4 to the negative 2 power is 1 over 4 squared is 1 over 64. So when you get small numbers here, you generally get negative numbers here. But if you try to do log base 4 of 0, that's going to be undefined, because there's no way you can raise 4 to some power and get 0. Anything you raise 4 to is going to be a positive number. And the same thing is true for like log base 4 of negative 16 is also undefined. This is a question I find interesting to do with no calculator. Log base 7 of 7 to the 35th power. Well, I don't want to calculate out 7 to the 35th power, and I don't need to, because the answer is going to be 35. This question is asking, to what power would I raise 7 to become this large number, 7 to the 35th power? It's like saying 7 to the what power equals 7 to the 35th, so the power has to be 35. Another question I find kind of interesting, something like this. Notice how this number and this number match up. 8 to the log base 8 of 97. Well, I don't know what log base 8 of 97 is. I know it's somewhere, around 2 point something, because log base 8 of 64 is 2, and log base, 8 to the third is a lot bigger than 97. Maybe it's 512. So it's 2 point something. But what? Well, I don't know. So how could I possibly know what 8 raised to the power is? To that power? Well, it's going to be 97. Because this is the number that 8 needs to get raised to become 97. And then I'm actually raising 8 to the power that 8 needs to get raised to become 97. So it becomes 97. And those I find those to be kind of thought-provoking questions. We can graph logarithmic functions like y equals log base 2 of x. One way I can do that is by making a chart. But I wouldn't want to just pick anything for x, because most things I don't know what log base 2 of them is. So I'm going to purposely, let's just call that b is the base, I'm going to purposely choose b squared, b, 1, that's number 1, 1 over b, which is 1/2, and 1 over b squared, which is 1/4. If I choose those as my 5 x values, then my y value is going to be 2, 1, 0, minus 1, minus 2. And if I graph those 5 points, 4, 2, 2, 1, 1, 0, 1/2 minus 1, and 1/4 minus 2. I'd end up with something like this. And if I continue it, it actually has 8, 3 as the next point on it. I'll put that one in also. But on the left, I'm going to have an asymptote, because I can't do log base 2 of 0, and anything really close to 0 is going to be really big negative, so we end up with a picture like that. It has a vertical asymptote. It does not have a horizontal asymptote. It gets kind of flat, but it goes up and up. Compare this, and one way to another way to draw this, if you don't like this method, is to compare it to y equals 2 to the x power. Because 2 to the x power has 0, 1, 1, 2, 2, 4, minus 1, comma 1/2, minus 2, comma 1/4. See, that one has a horizontal asymptote. And these two things are known as inverses of each other. Their graphs are the same reflected over the y equals x line. If 2, 4 is on y equals 2 to the x, then 4, 2 will be on the curve y equals log base 2 of x. So they're inverses of each other. And you could, if you wanted to, make a graph of this one first and just take each point on this graph and reflect it over the y equals x line by interchanging the x coordinate and the y coordinate. Just remember that the horizontal asymptote in the y equals 2 to the x, when you reflect that over the line y equals x, it becomes the vertical asymptote of the logarithmic curve. This is a log curve that's going to have some geometric transformations. The way I would do this one is I would start by first graphing y equals log base 2 of x. which, as we saw before, had a 1, 0, 2, 1, 4, 2, half, -1, and a quarter, -2. Then I would take each of those points and translate them 2 units to the left and 3 units down. And I would do it 1 point at a time. So from this 4, 2 point, I'd go 2 units to the left and 1, 2, 3 down. From the 2, 1 point, I'd go 2 units to the left and 1, 2, 3 down. From this 1, 0 point, I'd go 2 to the left and 1, 2, 3 down. Even this point at half, -1, I would go 2 to the left and 3 down. And even from this quarter, -2, I'd go 1, 2 to the left. Now the asymptote, which was the y-axis, it gets moved 2 to the left also. So the asymptote ends up over there. And when I graph it, get something like that. There are some properties of logarithms that I want to illustrate here. One is that here are 3 facts. 2 to the 5th is 32, so log base 2 of 32 is 5. 2 to the 3rd is 8, so log base 2 of 8 is 3. 2 to the 2nd is 4, so log base 2. This suggests a famous log rule, which is this: log base b of the product of 2 numbers, like 32 is the product of 8 times 4, is not, notice how 5 is not the product of 6 times of 3 and 2, but the sum. And that's a big rule: log base b of x plus log base b of y. It's kind of like the rule that when you multiply 2 numbers, 2 exponents, if you have the same base and you multiply the numbers together, you add the exponents together. Since log is kind of like an exponent, it's the exponent that b needs to get raised to. It has to do with that. Like 2 squared times 2 to the 3rd is 2 to the 2 plus 3. It's related to that. So that's a big log rule. Log base b of x to the n power is the same thing as log base b of x, x, x. There are n of these. And then according to that other rule, we could split it up into log base b of x plus log base b of x plus ... plus log base b of x. Again, n of these. But when you add together n of the same thing, it's the same thing as multiplying. And this rule is going to be extra useful. Basically says that if you have an exponent here, we're permitted to kind of bring it down so that it's in front of the log. That rule is very useful in solving equations where the unknown is the variable, is the exponent of that. So we don't know this. It's between 2 and 3, but what is it exactly? Well, in algebra, you can do stuff to both sides. You can add to both sides, subtract, multiply, divide. Well, another thing you can do to both sides is take the log of both sides. Now, this looks like it made it more complicated, but it's actually going to make it solvable, because now I can bring this exponent, using that log rule, I can bring this exponent down so that it's on sort of the same level as the log 8. Now this log 8 is just a number. It's some number less than 1. It's what would you have to raise 10 to become 8. It's some number. It serves as the coefficient of the x, kind of like if I said like x times 9 equals 27, you'd say, okay, I divide both sides by 9. So this is x times log 8 equals 97, so divide both sides by log 8. And your calculator has a log button, so you type those in and it becomes about 2.2. If your calculator lets you do log to other bases, you could just write the answer right away. You'd say x equals log base 8 of 97. And if your calculator has a log base 8 button or a function for it, it would get the answer right away. But if it doesn't, if all your calculator has is a log base 10 button, this is the way you could do it. Sometimes there's extra stuff. Oops, plus 5. That's a plus. Well, you need to isolate this expression. So we take away 5 from both sides. We get 3 times 8 to the x plus 1 equals 291. And you divide both sides by 3. Get 8 to the x plus 1 equals 97. Now if I do that thing from before, do the log. This time I take the whole x plus 1 and bring it in front of the log 8. Let's put parentheses around it. Log 97. Then you can divide both sides by log 8 and you get x plus 1 equals log 97 over log 8. We've already established that that's about 2.2, but we're not done yet, because this plus 1 that was over here originally is finally, he's the last guy to get taken care of, and you get 1.2. There is something called the change of base formula. It goes like this. If I were trying to solve a question like b to the x equals a, in other words, log base b of a is equal to x. And if I did it the long way by doing log of both sides, the x would come down, x log b equals log a, and x would be log a over log b. So x also equals this, so those are the same thing. So here's the change of base formula, log base b of a is equal to log a over log b. So if I'm doing a question like 8 to the x equals 97, and I know that's the same thing as log base 8 of 97, and if I know this rule, I could just do log base 10 of 97 over log base 10 of 8, and out comes my answer, which was 2.2. Incidentally, you don't have to take log base 10. I mean, it's the one on the calculator, so it's the one we use a lot, but I'll put a little c there to say that if you happen to have some other base you want to use besides base 10, that would work also. Doesn't matter, as long as you use the same base for the top and the bottom. I could do a word problem now where population of a country is 280 million in the year 2000. I'll just call 2000. And in 2016, the population was 323 million. And they want to know, when will the population become 500 million? So what you would do is, based on the previous lesson, we could calculate out it's y equals a times b to the x power. This is assuming asymptote at 0. When the y-intercept, that should say 0 to, these are switched around, 0 to 80. Sorry about that. So a actually becomes 280. And then if we take this other point, 323 equals 280 times b to the 16th power. B eventually becomes 1.009. So our equation is y equals 280 times 1.009 to the x power. Now that I have my formula that relates x and y, population to time, I can answer questions like, I could say when x equals 40, what's the value of y? That one I just plug in the x for, that's easy. But the harder question is if they tell us what y is and they want to know when will the population reach that. Well, now we have the ability to answer that question. I can say 500 equals 280 times 1.009 to the x power. Divide both sides by 280 and cancel a little. I could even divide both sides by 2. So I have 25 over 14 equals 1.009 to the x power. I can take the log of both sides. And then I could bring this x in front. So I have log 25 over 14 equals x times log 1.009. Divide both sides. That log 1.009, that's just an ugly looking coefficient. And when those cancel out, I think we end up with about 67 years. So that's what you can do. Those are some properties of logs and what you can do with them, including solving word problems like a population growth question. You can take a look at all the slides that happened in this 21-minute, 22-minute video lesson.